Today I'm going to talk about the gigabit per second laser-based visible light communications. And visible light communications, sometimes we call Li-Fi, VLC or Li-Fi. Again, I'm from King Abdullah University of Science and Technology. And in short, we always call our university as KAUST. Where is it located? We are quite close to Colorado, actually, not too far away from here. You are here, and we are in a place called Thual, which is quite close to Mecca and Medina. And Jeddah is the international airport. So it is a still a very new university. We are very young. It's about 13 years old or so, 12, 13 years old. It's a graduate school, so we only have master and PhD program in our school. It's a small school still. We have about 1,000 something. We're going to ramp up to about 2,000 students, but so far still very, very small. And faculty-wise, we only have about 200, but we focus very much on the science and engineering. All right, let's switch gear to the topic of our today's topic. Optical wireless communications. When we're talking about optical wireless communication, we very much using light sources to send signal and to communicate. And if you look at the spectrum, wireless optical communications, we are very much tapping on various different wavelength from infrared, the long wavelength side, go all the way to UV. And today we are going to focus very much on the visible light ranging from violet color, 400 nanometer spectrum, go all the way to about far red of about 700 nanometers wavelength. And if you look into the frequency that we'll be able to tap on, it very much ranging from few hundred gigahertz, go all the way to 30 pentahertz or so. So RF, we know that we use it quite well, we still use it very broadly and widely for our communications. And the available spectrum is about 300 gigahertz. And it had limited spectrum to be used because it has to be licensed and is very much regulated by the government. And for optical wireless communications, we have a way higher spectrum than the RF, and it's unlicensed. It means that anyone designing the system will be able to use it without going through any authority for approval. And under the bigger topic, the subset of the OWC or the optical wireless communication is the free space optical communication, or usually we call it as the FSO. So for SFO, we very much using laser in the near infrared band. And those are very, very well developed technology. Most of the component for FSO is very well developed by the optical fiber com. And today we are not going to talk much about those. And this involved the satellite to ground and etc. But what we are going to focus on is very much on the visible light communications. That is VLC. And again, the band that we are interested is for 400 to 700 nanometers. And this wavelength, since it is visible light, we'll be able to use this visible light to generate white color light for lighting as well. So when we are talking about Li-Fi, we are very much talking about integrating the communications capability or functions into the lighting system. So we can use our light bulb to send very high signal, very fast signal for mobile access. And we can also, integrate outdoor. One is indoor, the other one is outdoor, for example, street light. So that we'll be able to use it for communications as well. So a couple of the applications for visible light communication VLC, we always refer it to the last meter communication. It's not going to be a very, very long distance communications. One of the very niche applications, several niche applications that we can think about involve the aviations. On the plane, for example, we'll be able to, instead of having the cable wire everywhere, we hope that it can be integrated onto the lighting system so that passengers on the plane will be able to access to high-speed data, high-speed movie, for example, or even internet on the plane. And we talk a little bit about the home VLC that is indoor. That will be able to use it for integrating into our lighting system, be able to use it for our portable mobile devices, and etc. Hospital VLC. In the mall, we can that will help people to localize certain items, and in the hospital because it's no interference, so that be able to use it alongside with other high sensitive equipment in the hospital, for example. And of course, outdoor as well, be able to use it to complement the existing 4G or 5G for the future application. For example, the autonomous vehicle that require a lot of bandwidth. So that can be one of the possibility. So as a quick summary, well, VLC is very much RS. We can use it in the RF sensitive applications or area, and it's wireless. Another one that I do not talk will not talk about it in these particular presentations, but I would love to be able to talk about it in separate occasions. Is underwater Internet of Things. So by using similar technology, but apply it to underwater. We did quite a bit of work in this space, but since today's topic is only for VLC, so I'll focus very much on the Li-Fi and VLC, but not the underwater wireless optical communications. Yeah, very much talking about the data-hungry applications for VR, AR, and for dual illuminations and communications applications. This is the last slide that will talk about some of the prospect that VLC would be able to complement the existing communication technology for the smart city and for well, the current hot topic, metaverse. Autonomous vehicle, I believe if you own a Tesla today, we are very much talking about a autonomous level of about 3, from 1 to 5. 5 is fully autonomous. If you want to go all the way to the fully autonomous vehicle, 5 or so, the bandwidth per vehicle is quite large. We are very much talking about hundreds megabits per second or so. And of course, 5G will be able to provide that, but you still have to have a lot of all those antenna and everywhere in order to provide such a huge bandwidth for all the vehicle on the road. And being able to use optical method that might ease some of the RF technology, because optical usually be able to go up to gigabit per second without much problem. The other applications that is very much data hungry is the VR. We know that we're going to, well, at least for Facebook now change to, hello? Yeah, for Facebook, for example, begin to pitch metaverse. And that again is very much very power hungry, data hungry applications for our VR. The current 4G, for example, what we are using in our Wi-Fi is very much a few tens of megabits per second. This is the data from the United States, 12.6 megabits per second. That's the average bit rate that we'll be able to get. Latency is quite long because it's very much talking about 40 to 60 milliseconds. And of course, 5G, we hope to be able to push it down to a single digit, for example, 1 millisecond or so, but we're not quite there yet. And the other one would be the holographic display. Can go up to, depending on the size that you need to display, can go up to gigabit per second and terabit per second with very low latency, so that be able to create the image for the 3D holographic projections. All right, so how are we going to do it? We know the evolutions of the lighting system, right, from fire to fluorescent, and currently, thanks to the inventions of the LED, we now have LED light bulb, which is very energy efficient. But in our lab, we focus on using laser to generate white color light for lighting, and also using the same light bulb for very high speed VLC. So what are the advantages of laser lighting? If you, well, Chang-Ming Lee from Santa Barbara wrote a very good paper comparing this. If you look at if you want to create a 60-watt incandescence equivalent for LED technology, because LED is a spontaneous emission, so that you get light everywhere. It's not direction. You have to have multiple chip, and the footprint is quite large. It's 11 square millimeter or so. And for laser diode, because this is confined light, it's guided light as well. So essentially, you'll be able to get a single high power laser that occupy only about 0.3 square millimeter to do the 60-watt incandescent equivalent. As for the speed, the quantum efficiency, excuse me, this is the LED. LED, we have these physical limitations for LED. When you inject more current into the LED, it will give you a drop in external quantum efficiency. It means that once you inject more current into, more carrier into the LED, instead of giving you more light, indeed it gives you more light, but the efficiency drop, it also creates a lot of heat. And this effect is called efficiency droop. It's fairly significant. You'll be able to get from 70%, for example, go below 50% if you inject more current into it. So essentially, it's not a very efficient device. And when you have heat accumulating in the device, it means that you make the performance of the device degrade significantly. For laser, we do not see this. Laser, when you inject more current into it or carry into it, the external quantum efficiency stay pretty constant, so that you do not see any significant drop in the quantum efficiency. So that is comparing the efficiency between LED and laser diodes. So how fast can we modulate it? For LED, if you go back to the rate equations, still very much depending on the carrier lifetime of the device, and it is in the nanosecond. But for laser diodes, the photon lifetime is in picosecond. So also means that we usually have no problem to drive a semiconductor laser to beyond gigabit to get a bandwidth of gigahertz. And as for the LED, we always being limited by the carrier lifetime, which is only a few tens to the most hundreds of megahertz of bandwidth. Again, this paper is from Chang-Ming Lee, Santa Barbara, comparing the LED plus phosphor. So how do we generate the white color lighting system? We use blue color LED to excite on yellow color phosphor. Yellow phosphor is very slow. We're only talking about a few megahertz of bandwidth, although we can go up to a few tens of megahertz for LED. But for the white color light bulb, you more or less being able to get only, well, up to a few less than 10 megahertz or so of bandwidth. And this is only this LED without the phosphor can give a few tens or so. But for laser diode, this is a very early work back to 2015. And laser diode is a ferrite peroxide laser that they are using. You can easily get beyond gigahertz of bandwidth, even with phosphor, because you still have significant amount of light escape from the entire white lighting system. So the bandwidth of the white light generated by laser diode is not limited by the phosphor, the yellow phosphor that we are using. Right, some of the lighting system that we built, this is actually powered by a very, very low power laser excite onto a yellow phosphor to get this, just as a demo, the white color light. We use about 50 milliwatts of blue color laser diode to excite on the phosphor to get this light bulb. And this is another illustration of the white color laser light. And this case is 1 watt of laser diodes. And we send this light as far as about 50 meters or so. So essentially be able to use this light to send gigabit of signal up to a few tens of meters without much problem. But of course, in this experiment, I'm going to talk a little bit about this thing. Instead of using a receiver, a high-speed receiver, we use solar panel to harvest energy as well as to use it as a receiver. So compared to the LED light bulb, we find that we can, for laser lighting, we can easily go beyond 2 times of the throw distance. Throw means how far can the lighting system reach out to the other end. LED light bulb, if you take the LED car headlamp, for example, you'll be able to get up to about 400 meters or so. And for laser light, you can go up to about 800 to about 1 kilometer, which that is the throw distance for LED and laser diodes. It consumes less energy, about 30% less energy. And because we mentioned earlier on, and you can definitely get a very, very small footprint compared to LED. That again is something that we play about, not publishing it, but I think it's quite nice to work on this. This is, we try to see how far a throw that we be able to get by integrating onto the flashlight optics. And this is me, and this is in KAUST. We hold a 1000 lumens. We use about 3 watt of power, I think 3.5 watt of laser to get, no, sorry, more than that. I think it's 4 watts or 5 watt of power to get up to this white light that we generated. CRI is the color rendering index. We can reach up to about 90. And then CCT, we very much being able to tune the CCT from warm white to cool white. Warm white is below 3000 Kelvin, and anything above 350 or so Kelvin and on, that it will be called as cool white. Cool white is a bit more bluish color. And then warm white is just like sunrise, sunset. Part of color is more yellowish and it's more comfortable to eyes. And our maximum throw that we get is about 1000 meters. All right, let's get back to a bit more technical. Right, by using LED to send signal, then get the visible light communication. This idea was first proposed and coined by Professor Harold Haas. Well, that was back in not too long ago, actually. It's 2007, 2009 or so. He very much buy off-the-shelf LED and then try to send a certain signal, modulate it and try to send certain signal. And in these first 2 papers, he did not even mention about what is a bit rate, but they essentially kickstart the entire field of the so-called Li-Fi. Li-Fi also coined by Professor Harold Haas. Professor Harold Haas 2 years ago, I think 1.5 years now, have just moved to Strathclyde from Edinburgh. And then in the community, people begin to look at how to get more bit rate out of it. And this paper from Chinese Academy Sciences is among the early paper that managed to push it to beyond 500 megabit per second. In this case, of course, they're using a very, very high order modulations method to get to 682 megabit per second. So advantage of LED, they do have a lot of advantage, and lifetime is definitely one, and relatively compact, very compared to other methods. And disadvantage, we mentioned about this already, efficiency drop and still very much limited modulation bandwidth due to large capacitance because the chip size is big by itself. So to push the technology further to get into the gigabit per second, people has been looking into micro LED. Micro LED actually is very, very good technique to get into, because if string down the size of the LED into micron size, in this case, it's about 10 micron per piece or so. Being able to modulate it faster, that is well, reduce RC, you definitely being able to increase the speed. So this is those are the early work done by Grenoble, France, and etc. to push it to a very high bit rate. And then a very nice work that's published by Strathclyde, Martin Dawson, Kelly Anthony in Glasgow, and Richard, Dominic O'Brien in Oxford, to essentially go beyond several gigabit per second. They managed to demonstrate 5 gigabit per second or so by using the micro LED technology. And in our lab, we work on the rear system. We hope to be able to get into, well, the entire length of this probe is about 50 meters. So we leave behind 4 meters or so for equipment. We try to send 2D real-time digital video through the system. Because being able to use a longer throw is very advantageous, rather than being limited to the ceiling height, for example, or up to about 4 or 5 meters or so. And this is what we try to push for, is the distance. How far can we send the video? And in our case, we send a 2D. This is still very much LED, 2D, a 2K digital video by using APD. A bit diffuse line of sight is not exactly the line of sight, because the spot, the signal, the light that's sending from one end to another is still very much quite a diffuse light. So it's the DLOS, diffuse line of sight communications, by using a 3-watt blue LED technique. We also get into building a more realistic system that is actually for Lockheed Martin for their secure communications, by having by building 1 by we essentially want to scale to 1 by M communication system rather than 1-to-1. So in this case, we have server 1, and that's connected to the router. We want to have our client, that is the receiver, client 1 to communicate with client 2. And then we want to see how fast can we send the signal, of course, after through the entire loop of server, and then from the server 2, communicate directly with client 2. And the data rate that we managed to get is about 100 megabit per second. And latency, we managed to reduce to about 2 milliseconds with a throw distance of up to 3 meters or so. That at least is a first step to get into, well, instead of 1-to-1 communications by using light, how are we going to use 1 by N? So although this is only 1 by 2, but it's very much scalable to 1 by N. Right, let's talk about the laser-based visible light communications. There are a couple of challenges. We know that laser is very much a narrow band, narrow line width. So high-speed phosphor for, well, how to control the CRI. CRI, color rendering index. We know that sunlight will give us, or any black body radiation will give us a CRI of 100. 100 means that it covers most of the wavelength, right? And then CCT is the color temperature, whether it's warm or cool white. Warm white is a color that is very comfortable to our eye, because that is a bit yellowish. So how are we going to control those? And high-speed transmissions and receiver. We know that in near infrared, in 1310, 1550, those are quite mature technology developed for optical fiber comm, but there's no such thing for visible light transmitter and receiver quite yet. Omnidirectional. And if you want to have high-speed detections, the receiver has to be relatively small, right? And small means that you're not going to be able to receive the signal from very wide angle or the field of view. How are we going to increase the field of view so that we'll be able to detect the signal? So those become the key challenges for the laser communication, laser-based visible light communication. In our labs, we begin to look into laser-based communications back in 2015. This is very much a very good, quick demonstrations. we still use 450 laser to generate white color light after shining onto the yellow phosphor. So have the laser light get into the yellow phosphor, convert it, and then get a diffuser so that be able to diffuse light with lenses go into the APD. That is a very quick measurement technique to see how fast can we send white color light into this high frequency system. The color quality is not very good. CRI, we only get about 58. 58 means compared to 100, that is covering most of the wavelength, we still very much fall short. And it's still very much cool white. That's 700 something Kelvin. But we managed to get up to about 2 gigabit per second or so. So it means that if be able to get a very high quality white light, the bit rates that we can get from this particular method, meaning by using laser to excite on phosphor, we're still being able to get up to gigabit per second. So the subsequent experiment, we focus on improving the color quality. So it's color rendering index. What we are doing is use 405, that is violet color laser diodes, excite onto the red, green, and blue phosphor, so that be able to cover more wavelength for to increase the CRI to about 80. 80 is not too bad because most of our LED lamp we have between for the low cost LED lamp sometimes is about 60 something, go all the way to 70. So anything that above 80 or so, that is considered quite good color LED lamp. And again, we still keep this to above gigabit per second. So it's essentially from blue color, we go for the violet color and then use RGB phosphor to achieve this, to improve the CRI of the system and yet being able to get it, drive it up to about 1.5 gigabit per second. And this case, because just now we talk about phosphor, phosphor is very slow. So the bandwidth of phosphor typically is a few, up to tens or so, right? And in this case, we go for a new type of phosphor based on perovskite nanostructures. So for these perovskite nanostructures, it gives you a green phosphor. So tapping onto those by using excite, by using 450, there's a blue color laser. And we have the emissions from the phosphor for perovskite nanocrystal, and also the red color. So it means that we're now being able to cover most of the visible light spanning from 450 go all the way to about 680 or so. So by doing so, we managed to increase it to about 90. So as you can see, this is the light that we are generating, and it's about 90. 90 is a good number. It means that we are no longer limited by a narrow line width from the blue color laser, and being able to tune it to a bit warmer light. Again, as you can see here, and in this case we get it to above 1 gigahertz, gigabit per second as well for the data rate. Yep, this is the light that we are building. And then this again is just a hobby that we built together. The Li-Fi modem, we use a very low power laser to make this, to generate the white color light. Then from the server to client, and then one-to-one communications. And we managed to drive this particular simple demo up to about 2 gigabit per second. Those are the company that's using LED. Pure Li-Fi is from Professor Harold Hurst. They're still using LED, but now they're currently reporting very large number after working together with the SLD laser. That's another company that provide them with laser. They talk about 10 gigabit per second, but that was about 2 years ago before the SLD laser was acquired by Kyocera. But I think for their LED system, there's still a few few tens of megabit per second. And Firefly is another company that is in LED, maybe a leading role a little bit. They can go up to 700 megabit per second. And this company have just acquired by Signify. Signify is the company from Philip. Philip make a lot of white light bulb, and they have just been acquired by not just this 2019 or so was bought by Signify. That's Philips lighting. High-speed transmitter. Right. Again, when we are talking about so far we only use a simple ferric rod laser for communication. Ferric rod laser is a broad area laser that the speed is very much limited by the device structures because it's still very much a simple laser that we are building. But in our labs, we begin to look into a single frequency laser, that is the DFB or DBR laser, that be able to give us a very narrow line with a single frequency. And of course, other than the communication, the single frequency visible light laser can also be used for several other applications. For example, the advanced instrumentations, atomic clock, be able to use it to, now the atomic clock that we are using is very much to track strontium. You have to have a very, very narrow line laser of 461 or so, or calcium. You have to make it very narrow frequency 552 to track those, so that be able to make it tabletop rather than using a very, very big system to track those things. So laser diodes, if being able to do so, that will be highly attractive. And yeah, again, another focus of my lab is in underwater comm, and blue and green laser is needed in underwater communications. In the free space, outdoor particularly, one of our objective is to align our laser onto the Fraunhofer lines. Those are missing spectrum from the sunlight. For example, you be able to get 4x6, for example. These are a huge dip in the sun spectrum, so that be able to send signal under the bright sunlight without worrying about the interference from sunlight. And another wavelength is 518, for example, have similar effect because it's all those missing wavelength from the sun. So that is part of the objective. Gallium nitride is the material that we use to make the visible light laser. It's highly challenging to engineer those material because it's very tough material to process. For etching into grating, for example, you have to use dry etching. It is difficult to etch well. So a lot of damage will then incur into the material. So that would degrade the performance of the laser significantly. But over the year, well, since very early day, 1996 or so, people has been using very conventional way of etching and grating to get into the FD laser based on gallium nitride. It's always good to be number one, right? So this is after the not long after demonstrating the gallium nitride based laser, and people begin to look into it. But I will not go through all those things. But essentially, the very, very typical way of making the FB laser, try to do something similar to the indium phosphide or gallium arsenide based DBR or DFB laser. In our case, what we are doing is to make the ferric rod laser, and then instead of putting the grating directly on top or beneath the laser gain media or the quantum well sections, we put it at the side. So by doing so, instead of going into a very, very low order grating, first order or whatever, we go for very high order grating. So that's easier to fabricate. This case, I think we go for 30 something order in order to control the wavelength because we can afford it. This is a very long laser, and placing orders grating on top next to it in order to control the wavelength. What we are seeing here is the first DFB laser in the green color, because green colors, not too many people are looking into it, and give us very, very good signal to noise ratio. The side mode suppression ratio of above 35 dB or so. and 14 milliwatt of power, and being able to get the line width down to about 30 picometer. That is very much limited by our OSA, the optical spectrum analyzer, because we don't go for a very good spectrometer. So it's very much limited, but 31 picometer of line width is which is among the very good line width for the DFB laser. We also work on the so-called sky blue. Sky blue is the wavelength, right? Sky blue wavelength is about 480 or so. So by pushing it to using similar thing, and now we increased it to about 40 orders of DFB at the site, and then get into about 40 dB side mode suppression ratio to get a line width of about the same order of 35 picometer or so. Then try to modulate and see how fast can we modulate this single DFB laser. We managed to get about above 10 gigabit per second of modulation. Of course, in this case, we still stick to a fairly high order of modulation of 16 QAM or so. Super luminescent diodes, not many people are working on it, but let me explain what is super luminescent diode. We know what is laser, right? Laser is stimulated emissions, so that you'll be able to have population inversions, and all the energy is then focused on a single wavelength, that is the lasing actions. And we also know about the LED. LED is very much the spontaneous emissions, right? You can then get very broad spectrum, highly incoherent. The power is usually somewhat lower as compared to the population inversions type or the stimulated emissions type of laser. But for super luminescent is in between laser and LED, is operated in the mode of the so-called amplified spontaneous emission, or ASE. So in this case, you do not have you still very much have a broadening in line width, but it gives you a decent power, and it's not as coherent as laser, and it's not incoherent as LED. So that is something in between. Why is it so? Why do we look into this? The key objective is that laser, when people talking about a lighting system powered by laser, people tend to be afraid of the laser light. Although in Europe, people can use laser light bulb as the car headlamp. If you buy a very luxury BMW or Audi car, you'll be able to get the laser headlamp. But in US, it's still not allowed, just simply because laser just work. So super luminescent diodes will maybe balance both world, laser and LED. And one of the key technology to get into amplified spontaneous emissions, because it's a single pass devices, you have to have a mirror destroyed instead of having the ferrite rod. Instead of having a dual mirror for oscillation, we then tilted one side of the angle so that you only have a single pass device instead of the multiple pass. We are not the first one to work on it. It's simply in Navagan and Switzerland. They have, those are all from Switzerland. Excelos is also from Switzerland, etc. That's been looking into generating the super luminescent diode by using a very typical way of doing so, tilted angle and S banding to suppress lasing oscillation and etc. I will not go through in detail. What we are doing here is just basically tilt one of the angle from our laser chip by 12 degrees, so that although you still have the feedback from one of the facets to increase the power, but you do not have the oscillations built up in the cavity to form the cavity. Doing so, we'll be able to get enough power out of it. In this case, we managed to get a few hundreds of milliwatt of power out from our device for these devices. Right. We also use the other technique by having the saturable absorber. This is a saturable absorber that's a bit early work of 2016. And the key highlight is that we managed to get into, use it to generate white color light and get into a very good bit rates of beyond gigabit per second. And this work is by tilting the angle, tilting the facets to 12-degree angle to get into very high power of 470 milliwatt. 470 milliwatt, although it's low in terms of laser, but it is one of the highest optical power from the super luminescent diode. And again, we try to integrate into the remote phosphor plate to get a CRI that is above 80, and then tune it to about warmer color of about 3000 Kelvin or so. And get into the entire system. Of course, we subsequently grow, increase the CRI to about 80, to close to 90. And we show that although the performance is in between the LED and laser diodes, but we still manage to get a very good eye opening at 1 gigabit per second by using this particular technique. Again, for LED, we know that to not be able to do so quite easily by using a single chip to go up to gigabit per second. But in this case, using a single super luminescent diode, we manage to get to gigabit per second bit rate. Receiver, well, photodetector at the visible light is way more expensive than semiconductor laser. To get into a bandwidth of, say, 1 gigahertz of bandwidth of APD, that will cost us a few $100s, 800 to about 1,000, depending on which company you buy it from. But semiconductor laser, for very broad laser, we can get a few tens of dollars. That will give you a few hundreds up to about 1 watt of laser. So in order to get a very good photodetector, I think there's a need to further investigating into fabricating visible light photodetector. In terms of receiver, we know that for high-speed receiver, we have PMT. We also have silicon to cover this particular range, the visible range, by using APD. And in our lab, what we are looking into is by using gallium nitride-based structures to get into very narrow line width type of the photodetector. Although we just now we talk about the VLC, visible light communications, but another very important communication is in the UV regime, the ultraviolet spectrum. So if you look at the UV spectrum from 200, that is UVC, go all the way to about UVB. The responsivity for most of the silicon detector is very low, to almost negligible if you do not have a TIA, the trans-impedance amplifier integrated into it. So one of the objectives of my lab is to look into how to increase this UV, the responsivity at the UV region, from 200 to 400 is found. So this high-speed photodetector that my lab are working on, we built micro photodetector array for high speed. Again, we know that to reduce the RC, the resistance capacitance of a device, in order to increase the bandwidth, we need to use very small photodetector. So the idea of making it into micro photodetector array is that we will be able to use the small photodetector for high-speed detections. And also, since we want to detect light from a wider angle, so all those array would allow us to do so. So what we are doing is essentially when we detect by using electronic control, once we detect the high intensity, we will switch the rest of the element into the fourth quadrant. So instead of third quadrant, that is a photodetector, right? Change it to the fourth quadrant to harvest energy, so they can then focus onto the broad area detections, yet being able to give us very high speed detections. So that is the objective of the micro photodetector array. Well, this give us the the peak wavelength that can be detected. And by modulating it using 16 QAM, we managed to get up to about 3.2 gigabit per second by using this photodetector that we make. This is another photodetector that we built or we fabricate. Well, essentially the difference between the previous one and this one is this photodetector, we try to use the semi-polar gallium nitride substrate that is built onto the bulk gallium nitride substrate to get a higher quality. And 16 QAM gives us about 3-something gigabit. But I think for most of the system, a very simple way of modulating it is preferred. So in this case, we very much get into on-off keying, on-off keying or OK modulations to get to 1.55 gigabit per second. This work is to address the low responsivity issue at the UV regime for the standard silicon APD. So what we are doing here is by using down conversions method. Again, we use cesium lead bromide perovskite as a light converting material. So by using a 278 LED, we then go through the cesium lead bromide in order to convert into green color. Green color more or less being able to get into about 550 or so, be able to increase the responsivity significantly. So by doing so, through the light converting method, be able to increase the responsivity of a standard off-the-shelf APD, silicon APD by 4-fold at the UBC 270 nanometers. While UBC span from 200 nanometers to 280 nanometers. And UBC is something that is attractive because all the UBC is being absorbed by our ozone. So by being able to send any signal by using this band of wavelength, it means that we'll be able to get into a very low loss communication channel. And we demonstrate that using this technique, we'll be able to get convert a standard silicon-based APD to give us 34 megabit per second. This is one of the highest. Actually, this paper received the Outstanding Paper Award from Light last year. Right, to increase the area of detections, we also look into the scintillating fiber. Scintillating fiber is actually the organic dye that we introduce into a fiber material. So this case, we would have a ribbon of all those waveguides to enlarge the detections area and then trying to guide, well, when incident light get into the fiber, it will be converted into blue color, for example. And this light will then be guided to a small photodetector that we place at the end. So the detection surface can then be enlarged significantly. In fact, we developed this for underwater comm, but similar concept definitely can be done or can be implemented onto a visible light communications by using this as a light converting structures. Then you have a curtain of the fiber to do the detections for you, so that you do not need to have the array of photodetector that will increase the cost significantly. So doing so, though, we would not be able, because organic dye is somewhat slow, and we can only get to about 250 megabit per second. But again, the objective here is to have this system for underwater comm. Yeah, this paper, we use fiber bundle to make these particular structures and then take it down onto a photodetector to increase the field of view for detections. This is very broad wavelength coverage from UV, from visible go all the way to near infrared. And the bit rates is always easily can go beyond gigabit per second or so. Let me sum up. So I think my time is up. In the lab, I only talk about the visible light communication, but at KAUST, we do have the capability of working on semiconductor material growth and material integrations. We very much focus on the heterogeneous semiconductor integrations from now by having different type of material and figure out how to integrate them together. And either from communication system or any system, harvesting energy is always one of the objective. And we also work on various different way of harvesting energy for using the material that we grow in the lab, essentially. And of course, as of now, our main focus is still very much in the making devices in UV and in visible range, and then integrate onto the system for communication. Before end, I would like to promote a journal, and I think the journal that's for people in my generations, we know it quite well, which is IEEE Photonics Technology Letter. It is still giving us a very, very respectful impact factor. And the H index of nature photonic is 144, and the H index for PTL is 157. So it means the history of the journal is very much older, and it's still very much a rapid publication. So I hope that you consider this very, very nice journal that you can publish. It's very minimum cost compared to other open access. And if you look at this, the PTL is still very much in Q1 journal in most of the category. It's already 32 years of history. If you look into the optics and photonics journals, JQE started first, and then optics later, followed by JLT. Then is PTL. So used to be a very, very top journal, and is very. I will be taking over as the editor-in-chief of this journal, and I promise to cut back the publications time to below 50 days or so. So really, I'll strongly encourage you to consider this journal for your next paper. And if there's any question, write to me, and I'm more than happy to answer anything about the this wonderful journal. With this, I would like to end. Thank you very much. Well, of course, I thank my collaborators and thank my funding. Well, without funding, I don't think I can do much. So thank you very much indeed.